Hey everybody, okay, so we are kind of midway through chapter 23, maybe a little further than midway, so only got a couple more topics to talk about. Last time one of the things we talked about was the acetoacetic ester synthesis, and what it is it's a method to make methyl ketones, which are, what's a methyl ketone? It's a ketone with a methyl group on it, and like a pair of R groups, right? So we showed how this all worked. In a nutshell, it was start with this stuff called ethyl acetoacetate. Then we can, remember the proton's really acidic on the alpha position there, and so it's really easy to remove that proton and then like do an alkylation, like a SN2 alkylation. So it's like base takes off the proton, then you attach R, through Rx, take off the second proton, and then attach R prime X, and then you got this dialkylated beta keto ester. And then the kind of cool thing happened where we use acid, and acid kind of accomplishes two things. It hydrolyzes the ester to a acid, so you go from a beta keto ester to a beta keto acid, and it also kind of facilitates the decarboxylation, so the loss of that carbon, and we lose CO2. So the byproducts, the net byproducts of this reaction are going to be ethanol and CO2. I can try to maybe sneak them in there. Well, I can't really sneak them in too well, but ethanol and CO2 are being kicked out through this reaction. Okay. We did the mechanism of it. Let's kind of show that all here. What the key steps were: acid water results in the hydrolysis of the ester, and we even reviewed the mechanism of that. It was just, remember, it's like protonation of the ester, the water attacks, make ethanol a good leaving group, kick it off. It's called the reverse Fischer reaction, or reverse Fischer esterification. It's also called acid catalyzed ester cleavage, or you could say acid catalyzed ester hydrolysis. All of those mean the same thing. Then you get the beta keto acid, and then it just kind of flips up, and then the oxygen is able to swing up, grab the proton, decarboxylate, lose CO2, make an enol, and then enols can tautomerize to the keto forms using proton transfer, essentially. It's just a two-step mechanism that we learned in chapter 18. Okay. Okay, and then we also started the other one of these that's kind of related. This whole section 6 is like synthetic strategies or synthetic tricks. It's called the Malonic Estrogen synthesis. It's the same exact thing, except you end up with a carboxylic acid and 2 R groups. In that, it was kind of the one difference, obviously, was the starting material. Draw this out. Well, this is all from review from last time, so you have this all in your notes. But you start with this diester. It's a beta diester, diethyl melonate, and then same thing: base alkyl halide, base alkyl halide. Attaches your stuff through SN2 chemistry, and then we hydrolyze the diester to a diacid, and then it all falls apart to give the acid with the 2 R groups. And this is, as we concluded last time, how that all works. Both esters get lost. You lose 2 ethanols, so 2 ethanols are lost, right? In the hydrolysis, 2 ethanols are lost, and then you get the beta diacid, it flips up, and then maybe the funnest part of the mechanism is that the flipped up beta diacid, have one of the double bonds, grab the proton, and then electrons go in a circle to make the enol, the carboxylic acid enol, and then that tautomerizes to the carboxylic acid. Alright, so let's keep going with the Malonic Estrogen synthesis, which we now know about. So number 6 we're still calling is like synthetic tricks or synthetic strategies that use these beta dicarbonyls. Right, and we are on C again, which is Malonic Ester synthesis. And the Malonic Ester synthesis, of course, makes carboxylic acids with 1 or 2 R groups. You can, if you want, you can attach 1, but we can attach 2 as well. Okay, so let's just show an example of like how you might make something. So how would we make carboxylic acid with a benzene CH2 and an isobutyl group? And so, well, of course we're in the Malonic Ester synthesis section, but if we weren't, and you're just thinking about this, the way we know that it is a Malonic Ester synthesis is, oh, it's a carboxylic acid with 2 R groups on it. So that's a good dead giveaway that we're going to use a Malonic Ester synthesis. Okay. Now, what if it's a methyl ketone? Well, if it's a methyl ketone, then it would be the acetoacetic ester synthesis, right? Okay. Yeah, so now given the 2 R groups, it's just a matter of putting this all in that formula. So we would just start with diethyl melonate. I guess to do this, you need to know the structure of this. It's not that difficult. Diethyl melonate is again the diethyl ester with a CH2 in the middle. Okay, so now it's a 4-step process to attach the 2 things: base something, base something, and maybe we'll do benzyl, which phenyl CH2 first, benzyl bromide, and then maybe the other one we'll do isobutyl bromide, and that attaches those 2 things. Alright, so that's the benzyl, which is the phenyl CH2, that's the isobutyl, which is right there. Okay, and now it's just a matter of acid will cause and heat causes the ester hydrolysis and the decarboxylation, so you get to the final product then. Okay, so that would be HO. What's that? Okay. It's flipped around a little bit versus that. It's the same molecule, of course. Okay. And of course, let's just review for fun the decarboxylation mechanism. So mechanistically, I'm not going to show the diester hydrolysis because that's just a long, silly process. H3O, of course, causes the dihydrolysis, and you get the beta diacid. Okay, diester, diacid, diacid. And let's just review the mechanism of the decarboxylation one more time. So we just flip up one of the carboxylic acids. I usually just pick the right side one. Now you have a carboxylic acid flipped up. dot dot dot. Now you see that little 6-member ring? 1, 2, 3, 4, 5, 6. It's like a 6-member transition state, concerted mechanism. Grab the proton, make CO2, make an enol. So now we have the carboxylic acid enol. Right? And that just tautomerizes, I guess. Tautomerism is the behavior. It's a PT. Cool. So that is the just another example of the Malonic Ester synthesis. Okay. Okay, still on number 6. Still on C, which is Malonic Ester synthesis. And let's try another example to make this molecule. Five-member ring with a carboxylic acid, and we see that it's a disubstituted carboxylic acid, alpha disubstituted, because we have two things on the alpha position. The alpha position, of course, is that, right? There's two things, they just happen to be wrapped around. We did this kind of problem in the acetoacetic ester synthesis, but it was a methyl ketone, and I think it was a 6-member ring. But yeah, same idea. Okay, so I mean, all we got to do is to do this is visualize what what the alkyl halide is going to be, right? Is it a 1 alkyl halide or is it a alkyl halide? Well, and how many carbons will be on that alkyl halide? Well, we see the squiggly lines. Well, it's going to be there's a 5-member ring, but one of the carbons will be part of the diethyl melonate, so the alkyl halide will be 1, 2, 3, 4 carbons, right? Okay, so it'll be essentially a bromine, 4 carbons, bromine, right? Alright, so to do the whole thing, start with your diethyl melonate. And again, in this situation, what I do is I just say base, excess, because it's not like we're going to do this sequentially, like add one thing and then the other. We're just going to do it all at the same time. So now it's bromine, carbon, 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 carbon. So it's 4 carbons, I'm sorry. 2, 3, 4 carbons. Alright, that will make the diester with those 4 carbons attached. I'll show the intermediate in a second. And then acid will hydrolyze all the esters, cause the decarboxylation, and give us our product, which is pentane carboxylic acid. Cyclopentane carboxylic acid. Alright, yeah, the mechanism of this, I mean, it's not too exciting. Base takes proton, carbon attacks, then you get an intermediate. Carbon, 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 bromine. And then with that excess base that we have initially, the excess base will take the second proton off, and then that carbon will attack, and then it'll make the 1, 2, 3, 4, 5-member ring that we see there. Okay, and then of course with the acid step, it's the same old thing. You get the dicarboxylic acid. Two ethanols go away. Okay, and then we get the dicarboxylic acid. So beta diester, beta diacid. Flip up one of them. Still looks the same. Now you got the OH up top and the acetyl window down, dot dot dot. Do your concerted mechanism, arrow, arrow, arrow. Sometimes I draw that arrow around the other way, it doesn't matter, whatever, it's all the same. Lose the CO2. Now you get your, this guy. Just to eat all of that, it just tautomerizes. If you need help on that mechanism, you could ask me in office hours or something. Again, it's just essentially what I draw for is oxygen kicks in, double bond grabs a proton, and then you lose that proton. So it's a two-step process to transfer a proton essentially from the OH to the alpha position. And that's where that final proton winds up there. Okay? Cool. So that's another example of the Malonic Ester synthesis. Alright, still on number 6, synthetic tricks, I guess we'll just say. And reviewing these two reactions that we just learned, you know, if you're making a methyl ketone, we can use a retrosynthesis arrow, which just means a backward arrow essentially. You can make this from ethyl acetoacetate. And the ethyl acetoacetate, and the reaction is called the acetoacetic ester synthesis. Okay. Now, if you're making a carboxylic acid with two things on it, we can use our retrosynthesis arrow. And in this case, use the Malonic Ester synthesis, which is just, it's the same thing, but you start with a diester called diethyl melonate. The molecule is called diethyl melonate. The reaction is called the Malonic Ester synthesis. Of course, that's a beta keto ester. Top's a beta keto ester, and the bottom is not a beta keto ester, it's a beta diester, right? We have two esters that are beta to each other. Okay. One more example, just as a kind of a twist on this reaction. Say I really need to make a cyclohexanone with an R group on it like that. So I'm purposefully drawing it on the right because I'm going to do some stuff on the left. Say I really need to make that. You learned how to attach R groups to a ketone, right? Like you'd start maybe with cyclohexanone. We did learn that that's kind of hard actually. It looks so easy, right? To just take that, maybe treat it with LDA, good base, and then get that. The problem, if you remember from whenever chapter 18, I think, the problem was, well, you attach one, it might attach a second one, and you know, there's some issues there. We did learn another solution to this, which was making enamines. So that one solution we learned in chapter 18, I'll just write it up here, chapter 18, the enamine method, enamine, probably one of the quizzes even, was that you could start with the ketone, make an enamine, and enamines are really easy to make. It's a nitrogen with a double bond and a pair of R groups. If you make an enamine, enamines are nucleophilic, and then you can attach an R group really elegantly. So that's one way to do this. But now, given our what we now know, let's talk about another way to do it. So another way you can do this is essentially start with a molecule that looks like this, which is a beta keto ester. This is another very elegant way to do this. Okay, so this is just methyl ester, ethyl ester, whatever, it doesn't matter. Enamine was one elegant way to make this. This is going to be another elegant way to make it. So we can do base, like NaOCH3 or NaOET, whatever, and then Rx, right? That's super. This is very, very well behaved chemistry. You got a strongly acidic proton, base can take off the proton, then you throw in an alkyl halide, and then it puts the R group there. Okay? I'll put the R down here. Okay, so running out of space a little bit. Methyl, there we go. Okay. Alright, so you see what happened? Beta keto ester, base takes proton, attach an R group. Alright, that was very easy. And then we have another step here, which would be kind of like these malonic ester synthesis and acetoacetic ester synthesis, is you can treat this with acid, and then what's it going to do? What's H3O plus going to do to this molecule? Well, it's kind of the same as the acetoacetic ester synthesis, and kind of like the malonic. What's acid going to do? It's going to hydrolyze the ester to the beta keto acid, the R group there, whatever. Nah, keep it down there. R, whatever. And then what do we know about beta keto acids? They do that thing where it flips up and then it loses CO2, and then it basically would make this. Okay, so that's what I was trying to show, is that this is an alternate way that we can use to attach things to like a cyclic ketone. And it's elegant because there's no all the steps are well behaved, right? Okay. Okay, so these things are beta keto esters. Beta keto esters. What's this thing called? Beta keto acid. And of course here you lose CO2 through that mechanism we've done a bunch of times. Okay, one more question. How do you make a cyclic beta keto ester? That is like, how do we make this thing? How do you make any beta keto ester? Think about the beginning of this chapter. We learned a certain reaction could be used to make beta keto esters, right? That was the whole point of the early part of this chapter. Yeah, and it's also cyclic, and you can do this with a, how do we make it? The Dieckmann condensation, which is the intramolecular claisen, right? So we can make this bond from basically ester there and ester there, which is a claisen. Claisens are an ester reacting with an ester to make a beta keto ester. So you can make this from, essentially, how many carbons will this diester be? 1, 2, 3, 4, 5, 6, which would be like OME. 1, 2, 3, 4, 5. It's actually 7 carbons total, I think. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, and that's and here I'm using methyl esters. Sometimes I use ethyl esters. If I'm using methyl esters, I probably use OME instead of NaOET for various reasons. And then you always need the acid step for a claisen. Okay, so this could be a precursor for that. We could do a claisen on this dimethyl ester to make a beta keto ester, attach something at the alpha position, and then do the same kind of decarboxylation business to make a substituted cyclohexanone, right? Anything else to say about that? Yeah, the names of this. This is a claisen, of course. When you're converting a diester or a pair of esters to a beta keto ester, it's a claisen, right? This is an intramolecular claisen. And remember, the intramolecular claisen also had another name. It was the Dieckmann cyclization. Dieckmann cyclization. It was one of those reactions we did early in this chapter. Okay. All right. Good. All right. We're done with our little synthetic tricks section. Now we're doing beta dicarbonyls. Kind of one of the themes of this chapter, beta dicarbonyls, in the Michael reaction. So this is actually nothing new. You already know about the Michael reaction. You may have forgotten about it, but you do know it, or you did know it. What did we learn about the Michael reaction previously? Previously, you learned that if we have, I don't know, maybe a ketone, that we can use a strong base, and strong base could be NaOET, or also like LDA, any of those kind of strong bases that take off the proton. And then we can react with a Michael acceptor. I'm going to use this one for this example. Okay, so this is the Michael donor. This is the Michael acceptor. The donor is always the nucleophile, the acceptor is the electrophile. Okay, and essentially what we get is, what was the product of a Michael? A beta, 1,5-dicarbonyl. And by 1,5 I mean the relationship between the carbonyl 1 and carbonyl 2. 1, 2, 3, 4, 5, right? So 1,5-dicarbonyl. Okay, and what's the mechanism of this all? It's really easy. Base takes proton. We'll use NaOET for example. Makes a nice enolate. Still a Michael donor, but now it's like the activated Michael donor because it's a nucleophile. Nucleophilic enolate. And yeah, so now the donor attacks the acceptor. And so this goes there, this goes there, this goes there, this goes there. It attaches. I forgot step 3, which is like water. Let's add water in there. You need some kind of protonation step. So it's base, Michael acceptor, water. Alright? Because you make an enolate here. One, 2, 3, 4, 5. O minus. Cool. And then the water comes in to finish off this mechanism. OH or H2O. So now the enolate grabs a proton from water Cool. And then you get the product. All right? A 1,5-dicarbonyl. Remember also when we learned about this that sometimes a Michael will continue to do something called a Robinson. Remember that? We'll talk about Robinson in a second. But the trick to not doing a Robinson was something about the Michael acceptor, like basically that you don't have an alpha proton on the opposite side of the Michael acceptor, like a CH over here or something. There's a phenyl here, it's a benzene, so that's obviously there's no CH. If you do have a CH over here, then it'll do a Robinson, and we'll talk about Robinson in a second. Okay, so anyway, but this is the basic Michael. The basic Michael. So now we're going to do the same exact thing, but we're going to do it with a beta dicarbonyl. So it's actually just, it's really not too exciting. Let's just use our diethyl melonate. You know, so it's a nice beta diester. These things, we used it in the Malonic Estrogen synthesis, but we can also use it in the Michael reaction. So we'll use a nice kind of weak. You don't need a strong base here. NeOET does work for this, and we'll throw in. This is our Michael donor. We'll use the same Michael acceptor just to be boring. And water. Okay, and what's the product of a Michael reaction always going to be? This Michael acceptor. Michael donor, Michael acceptor. It's always going to be a 1,5-dicarbonyl. So it's essentially going to be that carbon attached there, and then we get our final product. Okay, there's the two esters, ester 1, ester 2. Alright, and now we have carbon, 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 phenyl. It's a 1,5-dicarbonyl. Okay. Is it a 1,5-dicarbonyl? 1, 2, 3, 4, 5. Yes, it is. 1, 2, 3, 4, 5. Okay, so yeah, and the mechanism is not too exciting, so I'll let you do it. Base takes proton. That makes the enolate, the ester enolate, so it's just an enolate, like we did above. This is the Michael donor enolate form. That attacks the same way. Then you get a ketone enolate, right? And then the water comes in to finish it off. Why is a ketone enolate? Because that ester enolate attacks this carbon, kicks electrons up, and you get a ketone enolate, and then the ketone enolate grabs a proton and you make the final product. The ketone enolate is kind of analogous to this ketone enolate up top. Alright. So yeah, that's an example of the Michael reaction applied to a beta dicarbonyl. Okay, so now we're still in this Michael reaction. Again, with the beta dicarbonyls. And we're not restricted to beta diesters. We can use other beta dicarbonyls also. Beta dicarbonyls. So this is a great way to attach almost any beta dicarbonyl to a Michael acceptor. So we'll just show a couple of them. We just showed like diethyl melonate. That was good. We can also use ethyl acetoacetate. Ethyl acetoacetate, which was also what we used in the acetoacetic ester synthesis, right? Great Michael donor. These are all good Michael donors. Any of these will work. Okay, what else? Dinitriles. We shouldn't make our nitriles bent. Keep them nice and linear. It's a pet peeve. No bent nitriles. Okay, and maybe a ketone next to a nitrile. All of these would work as a Michael donor. Okay, cool. Alright, and now, like we said, you can also use beta dicarbonyls in the Robinson. And the Robinson was sort of like the Michael with a few more steps, right? As we learned before. What are the 4 steps of a Robinson? It's good to kind of just memorize them. And I'll show an example. See, first you do a Michael, then you do proton transfer, or what I say, re-enolization. That's what I call it. Essentially moving the enolate from, because Michael creates an enolate, and the step B will move the enolate from one side to the other. Okay. And then step C was an intramolecular aldol, which is just an aldol within the same molecule. And then step D was dehydration, or you could say minus H2O. Dehydration. Okay. And remember that dehydration is always kind of like the last step of an aldol, because you always do aldol and then you always dehydrate and lose the water. But knowing these 4 steps, it's nice. We can go kind of backwards. Let's just show the sort of previous example and then the new example. So previous example that we learned before. We also did a quiz on this, so you can go review the quiz. Okay, so this is Michael donor, this is the Michael acceptor. The product of this is this. And in a nutshell, the Michael part used to make an enolate, and probably NaOET is the reagent. You make an enolate, it attacks, does the Michael onto the alkene here. Remember, the big trick to know when you have a Robinson is we have an alpha CH here. If you have an alpha CH, then you have the potential to do a Robinson. So this is on the other side of the the non-alkene side of the Michael acceptor. Right. So you look at the Michael acceptor, you see the alkene, you see the ketone. It's the other side. If you have an alpha CH, then you have the potential for a Robinson, because that's what step B is all about, right? Okay, so this carbon attacks. You make one enolate, and then step B is switches to the other side. You have another enolate, and then that enolate kind of swings back and attacks the ketone that you started with, and that's how you sort of build this ring. So I'm not going to review this. This is old. You can do this. You can review this all. I would recommend doing it. It might be useful for the final or something. Okay, so this is previous, and now let's do a new example, but using a beta dicarbonyl. It's actually the same exact concept, so not very exciting. Now with beta dicarbonyl, let's do, I'm going to give myself a lot of space. Actually, I'm going to even give myself even more space. Lots of space. Lots and lots of space. Okay. Alright, so I'm going to draw over here on the left a beta diketone. pair of methyls. Okay. And now that'll be the Michael donor, MD. And then the Michael acceptor will just be this molecule. Michael acceptor. Okay. And let's kind of step through the intermediates in the mechanism to make this molecule. Methyl, methyl, alkene, ketone, ketone. Alright, so we're going to go through those 4 steps. The Michael, proton transfer, and the aldol, and the dehydration. Okay, let's do it. Okay, so for the first step, it's just the Michael. But we gotta first take out the proton. We assume a reagent, NaOET, also I should have said that. Just a base, right? Alright, base takes proton. I'll just draw it this way. B dot dot takes proton and makes an enolate. Alright, what does that make? Enolate. I'm going to try really hard not to lose those 2 methyl groups. These 2 methyl groups. Let's see if I lose them. Oops, sorry. Okay, so yeah, base takes proton, makes an enolate. So now we have the enolate version of the Michael donor. Alright, now the enolate does the Michael reaction onto the Michael acceptor. So kick the electrons in. Let's make the nice arrow there. Kick the electrons in, and that remakes the ketone. And then this double bond goes and attacks that double bond to make a new enolate. Okay, this is all step A. Alright. Make an enolate and have the Michael donor attack the Michael acceptor. This is technically step A also. What do we got now? Keep everything oriented the same, that helps. Ketone, ketone, methyl, methyl. And you can start seeing that how this kind of will look sort of like the product here. Let's just double bond here. Okay. So these will be kind of oriented the same. So now we have the Michael donor attached to the Michael acceptor. So we got carbon, carbon, enolate, O minus, ethyl group. Oh, and I actually just noticed a problem. There's a methyl here missing too. I'm sorry. There we go. Alright. The reason I noticed that is because I saw that carbon and I'm like, where is it over there? There it is. Okay. Alright, so that was all step A. Make an enolate, attack. That was the Michael reaction. It's all step A. And what was step B? Step B is what? Step B is to I call it proton transfer or re-enolization. All you do is move your enolate from one side to the other. And so we just redraw this. Methyl, methyl. Ketone, we are 2 ketones, yeah. Carbon, carbon, methyl. There's our O minus. There's those 2 carbons. What am I missing? The enolate, right? Okay. That was step B. Really easy. Now step C was the intramolecular aldol, so now this just swings down and attacks that ketone. That is step C, the intramolecular aldol. Okay, now I'm going to assume also just maybe a little ethanol or something protonates the O-. That just saves us a step. So yes, like it does the aldol, and then we protonate the O- thing, and then we get the intermediate of a aldol. What's the intermediate of an aldol? It's a, well, we'll show it in a second. So we have this. The ring. Oh, sorry. No. Okay, sorry. You gotta be careful here. All right, let's see. We got a ketone here. I was trying to do too many things at once. We got our ketone. The ring is built here actually. And how big is the ring? It should be. It's always 6 carbons, so it should be 1, 2, 3, 4, 5, 6. So it's a 6-member ring, and of course we see a 6-member ring up top, so we know where we're going with this. Okay. All right. So 6-member ring. There's our 6-member ring. And what else is missing? Methyl is missing. What else is missing? This now is a ketone, which we see in the product. Anything else is missing? The methyl is missing. And thinking about the mechanism, if the enolate attacks that ketone, what's there then? And we're assuming that it's first an O-, and then we get a proton from ethanol or something. And that is this. And that's what I was trying to say is, what is the intermediate of an aldol? The intermediate of an aldol is a beta hydroxy ketone, and this is totally a beta hydroxy ketone. Ketone, alpha, beta. Beta hydroxy ketone. Okay, and what's the last step of an aldol, or in this case, last step of Robinson? Minus H2O, which is the loss of water, and of course you lose an OH, and you also lose this H. So you lose an OH and an H, and that's water, and that all goes away. Okay, we have that way of drawing this. I'll sneak it in there. This is how we did it back in the aldol chapter. Kind of draw the H like that. Remember this? And then we can kind of, this is not a mechanism, but it does show, oh, where's the water? There's the water, and it goes away. This is not what I call a mechanism, and if I ask for a mechanism, you shouldn't draw this. This is just a visual aid of like, okay, where's the H, where's the OH? And there it is. Alright, so we stepped through this whole Robinson example. You might want to practice this yourself. That's probably a good idea. I did this, well, I did all the steps. I did make a couple little corrections here and there, but this is how it looks in the end. Alright. Also my pen died, so I got a new pen. But there's the structure, and very cool Robinson example. And the key difference is we used a beta diketone as our Michael acceptor. Alright, so we're on number 8 now, which is still the Robinson. We're just going to finish that up with one last example. Robinson with beta dicarbonyls. And we'll just conclude by presenting an example that you can just try yourself. And it's how would you make this molecule by Robinson? it's just a good example of practicing those 4 steps, the A, B, C, and D, but we're going to do them kind of going backwards. So we have a 6-member ring, double bond, ethyl, 5-member ring, and a benzene. And an extra ketone. Okay. All right. So, how would you make this by Robinson? See, I mean, the way you approach this is you would do this 4 steps going backwards, and the last step's dehydration to make the alpha, beta, unsaturated ketone. So, probably going to be a hydroxy group right there. All right. Another thing, remember the Robinson only makes 1 size of rings, right? It never makes 5, it never makes 7, right? So that ring, the middle ring is a 5-member ring, it is not being made in the Robinson. What's likely, and pretty much guaranteed, is the left ring is made by the Robinson. This ring is made by the Robinson. That's a rule. You will never make anything but a 6-member ring by Robinson. Alright, so what I would do is, you could just try step D, figure out what step D is, draw the intermediate, and then step C, and then work your way back to the fundamental precursors of this synthesis. Alright? Okay. I think you guys are going to be sad about this, but I think we're actually on to the last topic. Number 9. So the last topic of this chapter, I think there's a couple other topics, but we like to usually stop on this one, is the concept of Acel Anion Equivalence, which is a kind of fun topic to end on because it's sort of a weird idea in terms of reactivity. Acel Anion Equivalence. What does this mean? So we're going to give it the sort of brief treatment. This could be a whole topic of a whole semester probably on Acel Anion Equivalence if we wanted it to be. Okay, so what is it? What is Acel? Acel usually means double bond O, right? Double bond O, carbon double bond O. Anion, we know what that means. It's negative charge, right? So the question to introduce this topic is, can we do this? Can we do this idea? Like, say we have an aldehyde, and is there a way we could just take a base, maybe mild base or the strongest base in the universe? I don't know. Can we use a base to grab that proton and then kick the electrons onto the carbon and leave an anion, right? Then you'd have a C double bond O dot dot negative. Okay. Can we do this? And I'll even put quotes around it, and I'll give a name of this concept. And what is it? It's an anion on an acyl carbon, so this would be an acyl anion. Can we do that? Is it possible to do this? I mean, and before we answer the yes or no, is it possible? Wouldn't it be cool if you could? Because then you could, attack stuff or whatever, right? Like, say we could do it, then we could do stuff like attack an Rx or something, and negative charge attacks R, kicks off X, and you got a ketone. Wouldn't that be cool? I don't know. I think I find it cool. You guys might not find it that exciting, but okay. So, supposing you could make this thing, yes, it would just attack and do kind of SN2 stuff, right? But back to the question: can it be made? Well, the problem is, and I'll just tell you right now, no, you cannot do it. The problem is that's not an acidic proton. This would only work if you had an acidic proton, and the pKa is so non-acidic that it's unmeasurable. There's no way you can do this at all. Okay, what is more likely to happen? If you have a base, it's not going to grab the aldehyde proton. It's going to grab the alpha proton, right? So more likely is you're going to make an enolate. You're not going to grab that non-acidic proton. You're going to make an enolate, and then it's going to probably self-aldol on itself, and you might get like I don't know. 3 plus 3 is 6, so it's 1, 2, 3, 4, 5, 6. Okay, so this is just an aldol reaction. Okay, so we can't do it because it's more likely to do aldol chemistry, and the reason is because the proton is not acidic, and because in order to be acidic, like say let's think about, like, if it did happen, why would anything be acidic? It's like, well, you make something that's usually resonance stabilized. This is not resonance stabilized. There's nothing to make this kind of happy or favored, and that's why it doesn't do this. But if it's totally impossible, why would I even be bringing it up? Because we're not talking about acyl anions, which is basically impossible. We're going to talk about acyl anion equivalents, so something that kind of acts like this idea, but is not exactly this idea. And when we do it, it's going to allow us to make, you know, ketones and things like that. We're going to have something that we can attack various R groups. Okay, so still on number 9, acyl anion equivalents, and acyl anions aren't really possible, but we do have this concept of acyl anion equivalents. We're going to do this, we're going to use thioacetals. And that was a chapter 17 topic. And this allows us to basically do everything we'd want with the concept of an acyl anion. What's a thioacetal? So we're going to use the same aldehyde that we were using before. And thioacetal was a kind of like an acetal. Acetal was like a pair of oxygens on a carbon. I'll show that in a second also. Thioacetal was a sulfur version of this, of an acetal. So this is a typical example of a thioacetal. Thioacetal. And how do you make it? Start with an aldehyde or ketone, and as we remember from chapter 17, you react this with ethane dithiol, which is like SH, carbon-carbon SH. If this was oxygens, that would be acetal, and this would be, you know, oxygens as well. Then we'd use acid catalysis, H+, but with the thioacetal, you use zinc chloride as your kind of a catalyst. Okay, we did talk about the mechanism of this, so I'm not going to review it. Go back and look in chapter 17. Something like the oxygen attacks zinc and then makes RSCC type thing, and then sulfur attacks. Okay. Anyway, so thioacetal will kind of be how we make our acyl anion equivalent. The pKa of a thioacetal is about 31. So that's actually, it's not super acidic, but it's acidic enough that we can rip it off with a strong base. And so the strong base we're going to use is butyllithium. Okay, and butyllithium will just rip off this proton. And that's going to make our acyl anion equivalent. Okay, so it kind of pushes the electron onto the carbon. Alright, so that the electron's going onto the carbon there. And what does that look like? So we rip off the proton, and now we got sulfur, carbon, carbon, dot dot negative. So this is our Acel anion equivalent. We'll see why and how we use it in a second. Why was that acidic at all? Because remember, 31 is a little more acidic than like a hydrocarbon or something. That's why butyl lithium just took it off. Why is this even acidic? Why is anything acidic? Because, you know, what makes things acidic in organic chemistry? Not the acid, but the conjugate base. And this has a resonance stabilized conjugate base. It's weird, and there's something special about sulfur. It's weird because this actually is resonance stabilized. How is that resonance stabilized? The dot dot negative can kick in and form a resonance structure that looks like this. That looks kind of weird, and it is a little weird. Because how many electrons are around? There's actually another pair of electrons. How many electrons are around sulfur? Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons around sulfur. Isn't that like an octet rule violation? It is, except that sulfur can expand its octet. Remember that whole thing? Sulfur can expand its octet beyond an octet, well, beyond 8 electrons. It can actually have 10 electrons around it, and it's that whole expanded octet phenomenon. So then this sulfur can, sorry, this double bond can move there, and net result is that we have a bunch of resonance structures. Okay? Where's the new negative charge? It's on that sulfur. Okay, so we have some resonance structures. So this is that sulfur expanded octet concept. And that gives us some more resonance structures, and that's why the carbon pKa is 31 and accessible to in butyl lithium. Now, what about normal acetal with oxygen? Can we do that? So normal acetal is the oxygen version of this. We don't use zinc, we use just proton, and then we get a normal acetal, right? Could we do the same thing with the in-butyl lithium? Like rip off that proton and make this? The answer is no, we can't, because this is not acidic. And this doesn't, there's no expanded octet here. So there's something special about sulfur that we're using. Whoops, expanded octet. We can't do the expanded octet thing with oxygen because it doesn't have an expanded octet. And that's why we can't do this all with acetals. We got to use the thioacetals. And the other thing, as we're going to see in a second, is once you got this, there's a whole bunch of things we can do. We can use this as a nucleophile, go attack stuff. And that's what's going to be cool about these acyl anion equivalents. Okay, so let's actually show a more real example now. Let's make another thioacetal. We'll use this simple aldehyde. Zinc chloride will make the thioacetal. Then we treat it with butyl lithium. Rips off the proton, this moderately acidic CH. Okay, and this is what we're calling our Acyl anion equivalent. We'll see why it's an Acyl anion equivalent. The point will be that, you know, once we go attack something with this, we can kind of return this back to a C double bond O, and that's why it's an acyl anion equivalent. Okay, so let's just show, like, kind of rapidly, like, what are the things we can do with this thing? Let's just show 4 different things we can do with it. Okay, well, first one is we can attack alkyl halides. It's a good SN2 style nucleophile, right? Negative charge attacks carbon, kicks off Br. Now we got a thioacetal. Right? It's a nice nucleophile. Good nuke. What else can we do with it? Maybe we can go attack an aldehyde. So aldehyde. Carbon aldehyde, 1, 2, 3, 4. A little bit of water. What's that going to make? That's going to attack, make an alcohol, and then we have those 4 carbons on there. Sulfur, sulfur. 1, 2, 3, 4. 1, 2, 3, 4. Okay, you can attack aldehydes. You can attack ketones. Oh yeah, hydroxy group. Sorry. We can attack a ketone. Like that. Acetone. We could maybe attack a epoxide. Remember, when you attack an epoxide, it attacks the terminal carbon, and that displaces the hydroxy to the neighboring carbon. So now it's going to look like that's all organic 1 stuff. We just made this bond, right? Okay, so those are some of the things we can attack: alkyl halides, aldehydes, ketones, and epoxides. All right. And then once we do that, we can return the thioacetal back to a ketone. So I'll just do it for this example. How do we do that? Remember that? That's chapter 17 also. How do we return a thioacetal back to a ketone? How do we do that? We can do that with not acid water. That's how you do it for an acetal. But for a thioacetal, it was water and mercury chloride, HgCl2. So mercury chloride was kind of the deep protection conditions, DP, to take off a thioacetal. Water, mercury. And to put it on, it was zinc chloride. Sometimes we abbreviate that P for protect. Okay. Bracket P to protect, bracket DP to deprotect. We're kind of using this protecting group as our acyl anion equivalent. I'm going to use this last example, this thioacetal that we made, just to show one other thing to remind you. Another reaction we learned. Is there a way to just wipe off that thioacetal? Let's make that. Remember that? You did learn that. Probably chapter 17, I think. Also chapter 17. Just wipe it off and make an alkane. And that was a H2 rainy nickel. R-A-N-E-Y nickel. It's just a formulation of nickel. And that just completely reduces off the thioacetal. Is there a bracket abbreviation for this? Well, it's a reduction, so we sometimes abbreviate reductions as bracket H bracket. So we can do a bracket H bracket, reduction, H2 rainy nickel of a thioacetal to an alkane also. Another fun example. It's a really versatile, kind of cool idea, so let's have fun with it. Is there a way we could like make this ketone make it and using thioacetals as acyl anion equivalents? And particularly, is there a way we can make this bond and that bond and just kind of magically just snap on the left piece, snap on the right piece? The answer is yes. So we can actually start with this chemical, which you can actually purchase even. It's like it's like formaldehyde with a thioacetal on it, right? Formaldehyde versus that. You could imagine just make this, but the point is that this is actually like a building block that we can just purchase and use. Okay, so how are we going to do this? All we got to do is attach the ethyl and attach this piece. So we're going to do, I don't know, we'll do the ethyl first. Butyl lithium, ethyl bromide. Snap on that ethyl piece. And then do the other one. Butyl lithium, and then it's like that benzene 2 carbons leaving group. pH for benzene. Alright. So now we got our ethyl and the other piece. And how do we just pop off that thing to make the ketone? We would just use what? Deprotect it with water and mercury chloride. Supposing we would just want to wipe it all off and make that, you could do that with bracket H bracket. What is it? H2 rainy nickel. Okay. We'll just do one last example like that. Basically, we're all done, but we're just having fun with this cool reaction that we just learned about. Let's do one more where we make something. Make this one. Let's make hydroxy group, an alpha hydroxy ketone. It's a ketone with an alpha hydroxy, not a beta hydroxy ketone that we've seen like in the aldol reaction. Let's make this guy, and we'll also assume we're gonna make this and we're gonna make that. We're gonna make those two connections. So this will be attached with probably an alkyl halide. And then this, though, is it going to be a ketone, an aldehyde, or an epoxide? Ketone, aldehyde, or epoxide? Well, we only have one R group, the methyl, so it's, and also the hydroxy group is directly connected, so not a ketone, not an epoxide, it's got to be an aldehyde. So let's just do the same kind of strategy. We'll start with this stuff. And I'm going to do butyl lithium. I'm going to attach the isobutyl group on first because that avoids having to protect the alcohol, and it just makes our life a little easier. So it's 4 carbons, 1, 2, 3, 4, and then a Br. Okay, that will attach the right side. And then how do we attach the left side? Butyl lithium, something and something. It's we said aldehyde, right? 2 carbon aldehyde, acetaldehyde. Always need that water step when we attack an aldehyde or ketone or epoxide. Alright, so that gives us HSS, whoops, sorry, now we got hydroxy group, ethyl. It's all flipped over, but we're all good now. What do we do to finish this off, to give us our final product? We just deprotect off that thioacetal with water and mercury chloride. And that is our last reaction. Okay, just another example of using the thioacetal as a acyl anion equivalent. Alright, I think I went over a couple minutes, but yeah. Okay, and then just remember there's going to be a review session, and the final exam or super quiz is kind of a cumulative thing, so don't skimp on the early material. I'll give some more guidance on the iLearn site, and I think the review session will help a lot too.